Welcome, my digital pathology trailblazers. We're on the third article, this place, non-generative AI, ML in medicine. ML is machine learning.
Learn about the newest digital pathology trends in science and industry. Meet the most interesting people in the niche and gain insights relevant to your own projects. Here is where pathology meets computer science. You are listening to the Digital Pathology Podcast with your host, Dr. Alexandra Zhurov.
And we are not yet halfway through, but getting there. The next one is going to be tough. It's going to be statistics. I need to really prepare for that one. Like the first three one, I have enough knowledge to basically teach it without too much preparation. This statistics, this is going to take some preparation. Other than we're doing the third paper are the authors of the papers. Well, not all of them, but the main initiators or of this whole series are these guys. Let me show you. It's going to be Liron, it's going to be Human, and it's going to be Matthew Hanna. They work together at University of Pittsburgh Medical School, and they are establishing AI Center of Excellence for Medicine. They were the main driving forces behind this series, and I managed to schedule a date to have them on the podcast. So be excited with me. I'm super excited to have them all on the podcast and talk about what they're like about the series, what was the goal of this, how did it happen that they did it, how long did it take, and all the stuff behind the scenes of writing a paper, which if you have ever, not even if you haven't written a paper, if you have read one, like it's a lot of work. It's tough. Anyway, so they did 7 of them. They are working on the Center of Excellence. They're being the Center of Excellence, and they're going to join me on the podcast. So I am super, super excited. So last time we talked about generative, and now we're talking about non-generative. So starting with this hierarchical structure of AI technologies. And today we're talking about non-generative AI. AI is the whole thing. Like everything that computers do can be described as AI. And so at the very beginning, we have machine learning. And then part of machine learning is deep learning. Then within deep learning, we have the foundation models, large language models, and vision models are within foundation models. And it can be both generative and non-generative. Last time we talked about generative. Now it's non-generative, meaning it doesn't make anything new. It predicts from data. And what can we use this non-generative application for? And I have the tendency that I think I have overcome, but maybe I have not overcome it yet, to be super excited about every new technology. And it's like, I don't know, let's call it new tech toy syndrome, where I see a new method and I'm like, oh, now I can forget about all this other stuff and I can just use this new method for everything. Never happens. And I keep being so excited, right? So doesn't matter. So what do I want to say with that? When the generative AI came on the scene, I was like, oh, we can like throw everything away from the non-generative. And of course, as I learn about the technology and about the limitations of the technology, I'm like, if we would pull this one approach and use it in combination, or this other approach, or maybe like you don't really need to deploy generative if your task at hand is so simple. So every time a new thing shows up, this happens to me, I kind of already control myself, but not always. I always get this excitement. So what can we use these non-generative AI foundation model tasks in pathology and medicine? We can use them for quality control, ensuring data quality, and detecting artifacts in host-site images. We can use it for classification. So here we have a couple of words that have kind of double context. Classification, for example, it's a normal word where you classify something, but it's also a concept in computer vision where you classify things, but by a computer, right? So a very common classification task, and these are called tasks. The things that the computer do. Classification task is identifying disease and detecting abnormalities based on the whole pathology or radiology image, cancer versus normal. So these are the algorithms that will help pathologists do something on the images. Then we have object detection. Like the name says, it detects objects. So it spots specific cells or features in pathology or medical images. And in computer vision tools, this object detection, there is something like a bounding box. So if I wanted to do object detection of this, if I was a computer, I would place a bounding box around it that would have, and each of them would have a bounding box, right? So this is a real thing, a bounding box. You basically place a box around the stuff that you're detecting. And also, this can be used for different cell detections. So Chi-6 quantification, the blood smear quantification, cell quantification, whenever you need an object, just to identify an object, you would use this. If you need to outline a region, you would use segmentation. And this is another computer vision word that means that you're going to be outlining a region of interest in medical images. For example, tumor in pathology images, where you have in the image analysis, you would do tumor stroma separation. If you only want to, for example, identify immune cells within the tumor or within the pentagon. But yeah, so segmentation for regions, for example, segmenting cancer, segmenting, I don't know, specific regions of an organ, segmenting vessels, something that you want to extract out of an image, but it's not an object, it's a region. So objects are the cells and regions are regions, right? And then we have something called anomaly detection, which when I heard about it, I was also super enthusiastic because I'm a toxicologic pathologist, and the job of a toxicologic pathologist is to, most of the stuff is normal, but not only in toxicologic pathology, also in diagnostic. Most of the stuff is normal. And then you want to train a model on normal so that it can tell you when it's abnormal. And I was like, this is a fantastic concept. Let's just do this. And I will keep just looking at the abnormal as long as I don't have to like visually screen. Well, it didn't perform that well because the very subtle changes that toxicologic pathologists evaluate are very subtle. So they don't look such an anomaly. You like hunt for the change. So these are the things you can do with the classical non-generative AI, and they are still like legitimate things to do where you can use these tools. And we can divide the AIs in supervised and unsupervised learning, and we're going to start with supervised learning. So supervised learning is with labels. What are labels? These are like names of things. This is a phone. So if I had an image and a label, it would be an image of this phone, and the label would be phone. And in medicine, label is going to be the diagnosis, for example, for an image, for a pathology image. It can be the diagnosis, it can be an annotation, it can be the whole report now with generative AI. So now the generative and non-generative is going to be intertwined, but the whole report can be a label for this image where you have descriptions, what's on this image. So basically pairs of something and then something that's telling you what that is. And in supervised learning, and the types that we have, there is classification and there is regression. And you can see on these images are brilliant. I love them. So classification, you have a bunch of dots, and then you want to divide them in some group, classify them into blues and oranges. So that is going to be classification. You classify them into one of the classes. Classes are the categories. And regression is, they are all like together. So you do a line around which these things are. So this is linear regression, and there are also different algorithms. So these are the types of supervised learning, and there are also different algorithms, which every time, so I've been doing this, or I've been in that space since 2016. Oh my goodness, that's like 9 years already. Crazy. Next year I can say I have a decade of experience in blah 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 in in this space. Anyway, but what I'm getting at is I remember when the random forest decision tree came out and we started using it in the tissue, the image analysis company I was working for, tumor stroma separation. And I saw a few images and they were so good. And I'm like, let's scrap again, right? Let's scrap all the other stuff that we did because this is so much better. And then on other images, it didn't perform. So then again, when deep learning came on the scene, I was like, oh no, this random forest is like so random. Let's not use it. Let's do deep learning. And then I learned about the limitations of deep learning. So before I tell you what it is all about, but I'm just, kind of making fun of myself to emphasize that there is a right tool for everything. There is no one tool for everything, right? I'm just super excited about stuff. So, and I think one thing is going to solve the problems of the world. So decision tree, where you basically make little decisions, support vector machine, and we have a little text about it. I'm going to go into that text with these because there is a little bit more explanation needed. We have linear and logistic regression, and linear, you can see that there's a line, and logistics, we have like two groups of points, and there is this S-curved. Then we have K nearest neighbor, and here is our neighbor in question, and we decided that it's actually closer to blue group, so we're going to instead of yellow. And the neural networks, so they are better than the other approaches for image analysis. They're not perfect, right? But they're definitely better. And here we have a real life example, I think, and segmentation, detection and segmentation and classification as well of digitized PAP test slide, right? So here we have what cells are here: normal cells, abnormal, metaplastic, and then we have also squamous cells and glandular cells. So squamous are from the surface or from the surface of the cervix in this case, but also we have glandular cells, endocervical and endometrial, and these are our classes, the categories, the classes. And there are different features of these things. They can be geometric features, nuclear to cytoplasmic ratio. We can have HPV status, and this deep neural network does feature detection, and deep neural network has this input layer. Then stuff is happening in between, and this is what is often referred to as the black box ability of AI. What's in the black box? You have input and then you have output, but what happened here? And things happen like convolutions and basically different computational calculations happen in there, and it's called neural network because these circles are called so-called neurons, and it resembles the connections in the brain. And then what we get from this output layer, we're going to have some quantification, we're going to have classification, we're going to detect the cells, and we're going to segment them. So that's what can happen with deep learning. And our deep learning neural networks were here, one of the common supervised algorithms. And here you give a lot of these examples. So that's going to be often a human labeling it. And in case of pathology, it's going to be a pathologist or a histotechnologist or whoever has the domain knowledge to consistently recognize and classify these cells. So let's talk a little bit about the theory. Decision trees. If you have any questions, let me know. Decision trees. This was a popular non-parametric choice for supervised machine learning in medicine and pathology. And building such tree-based machine learning models can predict patient outcomes, diagnose disease, and sometimes help identify new biomarkers. Do you notice there's no mention of can analyze images well? We used it for image analysis, but you take the newest thing and you check if it works. But yeah, these are still popular and useful. Then we have the support vector machines, and I'm going to be going back to the image so that you have, so decision tree was here. Then we have the support vector, right? And you see you have two groups of dots and some line in between, right? So let's go to theory of support vector machines. They excel at handling high dimension data and can be used for classification tasks. So the main goal is to find optimal boundaries, so-called hyperplane. So that was the line in the middle, hyperplane, that separates labeled data points of different classes. And in two-dimensional space, the hyperplane is a line, right? It doesn't have to be flat. It can be in the space, but then you have hyperplane that becomes a line. And data points closest to this line are referred to as support vectors. And then if a trained support vector machine model is presented with a completely new data point, it can be used to predict on which side of the hyperplane it will end up. So it can classify disease, and from continuous data, a regression approach can be used with support vector machines. So it's a combination. It's called support vector regression. This was regression, like checking, like kind of like retrospectively saying on which line these points are, around which line they are clustering. So you can combine this support vector, and you can probably combine everything, but that's the example we have here. And so let's talk a little bit about regression. Linear regression is denoted by a straight line, as we have seen, where logistic regression reveals, logistic is the other one. I'm going to be scrolling a little bit. So this one is the logistic. This one is an S-shaped curve, right? So linear is straight, logistic is S-shaped, and in contrast to linear regression tasks, logistic regression is often employed for binary or ordinal classification tasks, such as diagnosing the presence or absence of disease. And you had the points clustered above and points clustered below. Whereas the linear is going to be for continuous outcomes, such as blood pressure or glucose levels, right? Then we have K nearest neighbor, where the yellow dot became whatever it became, blue, I think. Yeah, we decided it's blue because it's closer to the blues. And this can be employed for classification and regression tasks. And K nearest neighbor model does not require a training phase. And they are also sometimes called lazy algorithms because computation is delayed until the prediction phase. That means that the computation is expensive because it's so delayed. And what can we use it for? For diagnose, classify. So here, see, they often say this diagnose, classify together. The classify is in brackets because diagnose is medical term, classify is going to be computer vision term. I have it in my book, a little diagram. I call it computer vision to pathology vision translation with giraffe images. If you have the book, it's on page 77, the giraffes, right? And this giraffe has just a box around all the giraffes. And this is a classification, it's classifying these are giraffes. Here, this one has a bounding box around each of the giraffes. There are 3. So this is object detection. Then you have all the giraffes together. We actually delineated the giraffes. So that's going to be the segmentation. We segmented them. And here, a certain type of segmentation, semantic segmentation. And here we actually segmented out every single giraffe, which is called instance segmentation. So these are the computer vision terms that you use to solve pathology problems, and pathology problems will be structures of interest, which are the dots and cells, and tasks of interest. In structures, we will have regions, and objects, we will have cells. And next time, if I want to show it, I'm going to prepare it in the digital version. But if you have the digital, you can get the digital version on digitalpathologyplace.com. There's like a big button, and you can just download this book for free right now if you want to. And then we have the neural networks, the almost magic. And neural networks, it's okay. It was we had a good image for this one. Application and performance of supervised learning models. We're going to talk about performance next week, but let's talk about the application. What can we use these models for? And like, how will you use it before we dive into it? Like, how will you use it as a pathologist? Like now you're going to be going to your IT people or to your computational pathology team and saying, oh, let's use regression for this and let's use this one for that. I wouldn't do it, but because, I'm not a computer scientist, but I can now constructively discuss different approaches, because I have the knowledge of the pathology tasks and what I want, like what do I want to get, what information do I want to get, and I know the names of the tools and what those tools are good for, and I can now explain to my computational pathology team, hey, this is a task at hand, these are the computer vision terms of the things that I want to achieve. Which approach do you think is best? Maybe that one, maybe some other one, maybe don't use random forest for tumor stroma separation. At least when I was doing this, it didn't work that well. But anyway, the example is like you need to have enough background knowledge to work in a multidisciplinary team, and digital pathology team is a multidisciplinary team. And we are part of this team, so we need to know how to talk to others. And what can we use the stuff for? So, for example, regression models generating continuous numerical values output can be trained on a data set of patient demographics, medical history, laboratory test results, along with, for example, cost of each test, and then labs can predict cost savings, right, from this kind of stuff. In pathology, the supervised machine learning is used for classification models, discrete class outputs that diagnose disease from labeled data. And the convolutional neural networks have been a cornerstone of modern AI within image classification studies, right? So both radiology, pathology, you want to screen, you want to say benign, malignant, cancer, no cancer. This is going to be classification. The method is the leverage is going to be convolutional neural networks, and because they can convert pixel data from images into progressively higher order visual features over the course of sequential convolution and pooling steps, and these steps are what is happening in the black box. And then we have unsupervised learning. So the supervised was with labels, unsupervised is without labels. And what do we have here? We have clustering, we have dimensionality reduction, and anomaly detection. Clustering, that we cluster some data points into groups, right? And in an unsupervised fashion, these groups are being selected. And I mean, I would do this group as well here. Yeah, probably. I will do the same. I will do the same as the algorithm does. And now we have 3 groups, and we can check, okay, what do they have in common? Do they have some gene expression in common? Do they have some test results? Based on, the data that you have, the algorithm is going to cluster them based on this information. Sometimes we have a lot of information, and not all of this information is relevant. So then dimensionality reduction would be something that could be used, and anomaly detection that I still believe it's going to get better, and then we can detect all these red dots even if they're very subtly abnormal, but that's an option as well. So the model only knows normals and flags everything that is abnormal. And the algorithms used here is k-means clustering, so making these clusters, principal component analysis. So here you figure out which groups these belong to, so-called principal component analysis. TISNA, one time I remembered actually a way of visualizing stuff like 3D relationships between data into a 2D plane. TISNA and TISNA plot. This is a TISNA plot. So clustering is going to group similar data points into clusters. Easy name, right? And based on their feature similarities, and this is fun. Fun. It's interesting. Randomly initializing k-centroids or cluster centers. And the keyword here is randomly. So it just like randomly initiates a center of a cluster and makes a cluster, which brings me to something about the unsupervised methods, is that it's not always easy to interpret why this was clustered together. You have to investigate, does it make sense, or is it being clustered based on irrelevant information or relevant, and which kind of information that takes us again to the explainability aspect of AI. In the supervised learning, there is a label, so you can compare it to the label, whereas in unsupervised, it's just figuring out which data belongs together. And you can then, as a researcher, you need to check, does it make sense? So in pathology has been applied to identify subtypes of disease, such as different cancer subtypes, patient subgroups with distinct clinical features of gene expression profiles. And the cool thing is that it can enable researchers and clinicians to uncover hidden patterns in different data sets. So if the data is if there is a lot of data, if this is a multidimensional, uncovering these patterns with your eyes or with your own mind is difficult. So you has leverage. And then the dimensionality reduction, also name says it all, reduce the number of dimensions, features in relation to original numbers. So basically eliminate everything that does not give you additional information to classify this data into categories. So while preserving the most important information. And so, for example, this is used to simplify AI models, compress data, reduce noise, improve performance, prevent overfitting, and reduce computational costs. And there is a trend or tendency that I'm seeing is, and this is often mentioned as a drawback. So the trend that I'm seeing, I think it's just a general tech trend that's happening, and then it's entering pathology AI world as well, that you like have this, it's actually everywhere, like life is a funnel. You have a highly computationally, how do you say, like that consume a lot of computational resources, and then an algorithm that consumes a lot of resources, and then you figure out how to streamline it, how to get the, like with this dimensionality reduction, you have a bunch of data that classifies it into something. Oh, can it use less data to get the same result? Can it use less computation to get the same result? Can it like not use the whole image at one time, but stream the image, and different ways to make these new computational discoveries lean, which is super important in medicine, not only, but in general, to put it in devices that have less computational power than computers and servers and things like that. So very important for medical devices to lean and trim off the unnecessary computational resources that are being used. Then we had our anomaly detection, outlier detection, which is unsupervised algorithms used to identify outliers. And this can be applied to pinpoint unusual patient records with a particular health issue, error in data entry, detect rare genetic mutations, identify errors, or flag abnormal lab results. So you immediately have something flagged, right, for further workup. Super useful. And let's look at here. We have the fully supervised learning, weakly supervised learning, and self-supervised learning. Let's start with fully supervised. Who has done annotations in this group? Have you annotated pathology images or any kind of like images, and not just hours at a time? Then you know why I'm making faces. And this is also the bottleneck of this approach. It's blessing and a curse at the same time, because blessing, you have an expert, or maybe you have some other orthogonal label, which is fantastic because you then don't have to have a human label stuff, but then you have a different cost associated, pros and cons of everything. But basically, this is going to be a slide plus an annotation or region of interest labels. And then you sample regions of interest using annotation, and then you have a predictor, and then you update this predictor using more regional, more annotations. So you give the model some annotations, then it trains a little bit, you see where it is making mistakes, you give more annotations, and then you can basically train a very good image analysis model. But if you want to use less human resources and not annotate so much, you can just use slide label and the slide label. So what's going to be the slide label? The slide label is going to be the diagnosis of the cancer that's on the slide, or like a case label where you have a bunch of slides together. Not all of them have cancer, but in general, the case has cancer. And then here we're going to use attention mechanism, and then the model is going to predict the slide, and it's going to go back to these predictions and update them as it trains. So this is the weekly supervised. And then we have self-supervised things. Well, I don't know if it helped, but what I want to say is that self-supervised learning basically eliminates the person labeling. I mean, it's a blessing and a curse. It's a tedious task, and you do need high quality data. So you do need to put some effort into it if you want to have a good model at the end of the process. And the more data you feed the model, the better. So the more you annotate, the better. The more you annotate, the more tired you are. And, I guess that's life. That's okay. Anyway, so self-supervised learning, we have the slide tiles, we have perturbation, perturbed slide and tile. So what did we have? Okay, here it had the yellow and here it has green. Then we have an encoder model, training loss, no label, and downstream use may require further training. And here it's basically matching stuff and also reconstructing stuff. So it didn't match circle and this other thing, but it matched the two stars. And then it's reconstructing. And the update encoder model using loss function that do not need class labels. And this borders on magic for me, but it's not magic. It's just the new computational ways of doing things, which I love, because in the last 2 years, I would say, maybe even more, but in the time when, so there was deep learning first that I learned about. It was before, but I learned about it like 2017, 18, and that bordered on magic for image analysis. But then the large language models came out in 2021, 2022. And I'm like, okay, if there is something that's not working right now in terms of AI, I don't have to get frustrated. I just need to wait, because those people are like constantly iterating and figuring out how to make these things better. And sure enough, there was something that I think it was the molecular prediction from images, because you can have molecular information as a label and then have a predictor of molecular stuff in an image. And I started seeing these publications. I'm like, okay, you just wait, keep following this field, and they will come up with something cool, a cool method. And then us as the scientists, pathologists, healthcare professionals, and whatever expertise we have, being aware of those methods, we know how to leverage it for our fields. So digital pathology and non-generative AI machine learning leverages whole slide images, right? We know it leverages whole slide images. As we said, can be labeled linking the slide with diagnosis or metadata. And metadata is basically data about data. So it can be patient demographics, clinical findings, tumor grade, stage, immunohistochemical results, response to therapy, and you name it. You can figure out what other data can be there. And then the term of annotation refers to process of marking or labeling specific structures, cells, mitotic figures. Oh my goodness, can you imagine sitting for 5 hours and marking mitotic figures? And people did that, and they did that well, and then came with a good algorithm for mitotic figures. And these annotations can be performed using digital tools. And when we have the annotation workshop, and if you have some data that is that can be shown and you would like me to do an annotation session on your data, and we can do it, in QPath, or if you're a vendor, we can do it in your software as well. And then you can reach out to me and we can organize that and do some. That's going to be a fun annotation session. I know I'm complaining about those annotation all the time. But on the other hand, you can put music on and you can hang out while annotating, and that's what we can do. So yeah, digital tools, overlaying bounding boxes, depending on what the task is, right? Different colors on H&E images can be done in open source, which QPath is the main open source, or commercial tools, V7 is one. And then you can export those annotations in text format, for example, JSON and XML. So here I need to highlight that, guys, because what I'm seeing, well, what I have seen so far, those annotation efforts like basically get embedded into the model, but you can annotation is data. And I don't think at the beginning of this process we were treating it as data that can be reused, and they would just like go into the proprietary software where the annotations were done, train the model was nice, good, perfect. You change the software, your annotations are gone, you need to start the effort from scratch. So my big ask to everybody who's annotating, if you can keep it as data that's reusable for different platforms, do it, because it's thousands of hours of specialist time, and it's like, I don't know, energy sunk into it, and then it's used once for one model and then it's gone and you have to redo it. And I've been doing that several times, like redoing. We should store them. Now the standardization for slide formats is better than for annotations, but if there's an option to store them and reuse them, let's start doing this, because it's very time consuming and subject to human interpretation, right? So let's treat our annotations as the precious data that it is. And let's talk a little bit about the future emerging paradigms in AI. Obviously foundation models, and there's going to be, you can see, we're going to be talking about it. We're just session 3. There is more, but foundation models are emerging technology, multi-model tasks that can involve variety of data types in medicine. And we said that the main categories would be image, text, and then we have genomic data, image, text, tabular data. I think genomic would be in tabular data. And combining these all from different disciplines would be. But what I wanted to emphasize here, and then multimodality, I want to tell you some names. Sometimes people ask me, oh, what do you think about histomics? And I'm like, what is histomics? So here it defines that algorithms that merely extract only select features from histopathology slide were called histomics, to those able to analyze hierarchy of novel features in entire whole slide images called pathomics or tissue phenomics. So I think tissue phenomics was invented by the company I was working for, by the Finians. Tissue phenomics. I think we had a symposium, tissue phenomics. But yeah, basically like hierarchy of different features. Next generation histomorphometry, like a lot of terms, but basically what they want to say, different data types, including the image data and combinations, right? Another piece of magic, vision transformers. Don't take the piece of magic literally, but these models, these ways of analyzing images, self-attention mechanism, and they can perform both patch level and slide level image classification, segmentation, and object detection. So they still need to divide images into patches, but what they can do after each patch is linearly embedded into a vector, positional information gets added to retain the spatial relationships between patches. I think this is novel. It wasn't the case before. It definitely wasn't the case for multiple instance learning, where you would tile an image into patches and then like let the model predict, is it cancer image or not, and it would have to sort, and there can be just one patch that has cancer. So anyway, the transformers do get the patch location information. And the next revolution that I'm seeing happen in consumer AI will be AI orchestration tasks, also in medicine. So yeah, AI orchestration, combination of text, image, and multi-omics data. And then in addition, as noted earlier, the classic non-generative foundation models are of great value, and they are of great value in combinations. And what combinations, like we will figure out what combinations, what makes sense, where does it make sense to combine classical with generative, non-generative, with generative, classical, with deep learning, and all these things. And the heart wants to show you that ultimately, the most likely best solution for a responsible AI approach is one that simplifies the approaches as much as possible, but also may employ a combination of traditional and advanced approaches, with or without generative AI, in addressing the task at hand. And so that's something to pay attention to, especially in marketing messages where they say, drop everything else, this is the new thing on the block and just use this. You know what? There is a reason why handymen have a lot of tools in their toolboxes, right? And that counts for AI and for science as well. I recently talked to a group of toxicological pathologists dealing with molecular pathology, and that was one. I was a podcast host for a TXP podcast from the Toxicological Pathology Journal, and one of my questions is there the main method. It was kind of like I knew there's no main method, no solution that solves everything, but I asked them, is there like the one thing that people now should be using? And they say no. They say basically the same. You have your problem and you need to pick the right tool to solve your problem. What about the representativity when one patient has multiple slides and tumor type and the consequences of the predictions? It should detect multiple tumor types. So it depends like how we use. Let me rephrase the question, but basically when we have the non-generative, non-foundation models, okay, and she's talking about the case with heterogeneous tumors which have multiple divergent differentiation. Do you have experience on that? So I don't have experience, but I'm gonna present you a concept that could be applied, or like the pattern that I'm seeing. So when those algorithms are being developed, those non-generative AI, non-foundation models, or like non-generative AI foundation models, they have very narrow applications. So it needs to be fit for purpose. And I think we had one publication where they developed an algorithm that will check the data for you and say, oh, is this data good for whatever your algorithm is going to detect? Let's do it at a very high level. If there is an algorithm that does breast cancer, and there is a certain types of breast cancer that it was trained on, it's not going to perform on a heterogeneous tumor that has multiple components, right? So the options, there are two options, assuming that option that I just mentioned from the literature is available. You kind of screen the data with whatever method of data screening you have to check if the tool that you have is going to perform on this data. If it will not perform, don't use the tool. Meaning it either goes back to the pathologist or it goes to another algorithm if we have one, right? But that would require upfront knowledge or screening. Okay, do we have the tools that can be used for those images, right? And if we don't, then those images or those cases are set aside as like specialty cases or something that must be reviewed by a pathologist. And that's how I would approach it, because there's no point in using a tool that's not going to be good for the job. I'm afraid in pharma R&D is quite difficult, weekly or self-supervised learning methods. Yes, I think so too. So I was, of course, that was in 2019 where I saw the first anomaly detection, and I was like, oh, now that's going to be the next thing. And then it didn't perform because pharma R&D, because ToxPath is a different, like the different visual presentation of changes. Digital pathology trailblazer. And I want to show you something before we go, in case you want to check out and do some shopping, because our store, Digital Pathology Store, is live. Here, this QR code, DPP Store, you can check it out. So I'm just telling you, it's beta version, you know, it's a work in progress, but I thought if you're interested in checking out the courses, checking out little things like these earrings, you can check out the store. You can also give me feedback on what you would like to see there, what is like totally off, because as I'm saying, this is work in progress, and I would love for you to go there and check it out and let me know what you think. And I talk to you in the next episode.